All right. So how is everyone today? Good, I hope. All right. So last time we were talking about money, and so we're still talking about money.
What's our $2 time?
Sorry?
What was it, $2 or $5 that we were watching for last class?
Oh yeah, $1, and it grew into $E, natural number dollars.
So like $2.71.
1 cent, yeah. The 10th. Okay. So just to bring us back into that idea, to remind you of these things, there's two models. There's the discrete compound interest model. You can look at the previous lecture notes to understand all of the parameters, but just here's the model. A is P multiplied by 1 plus R over N to exponent NT. Sometimes, often, you want A to be solved for, but sometimes you want P to be solved for. So if instead of solving for A, we could solve for P, and we could do that by dividing both sides by that thing there, so that you'd have P is equal to A divided by 1 plus R over N to exponent NT. But it'd be nice if we could write just like this one, we could write it like that. Is there some way we could move this denominator up to the numerator? Well, what's the cost of moving a denominator to a numerator? Well, we could like reciprocate both sides. That would work, but I don't want to do that. I want P to remain as it is and A to remain as it is, but I want to somehow move that up. Something like that. We'll negate the exponent, right? So then, in particular, we could write P is A multiplied by 1 plus R over N, but now with exponent negative NT. So what I want you to see from this, I'm just copying that formula down. Is that these two formulas are essentially the same, except this funny looking factor has moved side to side, and for this one in particular, the exponent is negative. Okay, that's for discrete compound interest. Then the discrete case, that's sort of like the realistic case. That's the case where there's like a real connection to reality, because well, when you have interest payments, those are compounded at discrete events, usually once a month, like on the 1st or the 15th or whatever. So that's what this represents. Then, we went through the thought experiment, the Bank of Math 1326, and said, oh, okay, well, you're allowed to have a principal deposit of $1, an interest rate of 100%, the contract time, meaning T, has to be exactly 1 year. That has the effect of making almost all of the parameters 1. And then if you let n go to infinity, that's conceptually that's saying let's let the number of compoundings become infinite, right? More than once a month, more than once a week, more than once a second, okay? Continuous. So this is the continuous compound interest model. And again, the main idea here is just that we let the number of compoundings per period, n, go to infinity. When you do that, the model becomes this. A is equal to p multiplied by the exponential of RT. And for reasons that are obvious, this is often called the PERT formula. All right, but just like sometimes it's, this model has A is solved for, sometimes you want to solve for P. So having looked at that above, I suspect you can just tell me what the answer is. What is P? Very good. Which can be obtained in exactly the same way, right? You just take that one and then divide, then you have A over exponential RT. But then to get to exponential RT in the numerator, you negate the exponent. All right. So we have a discrete compound interest and continuous compound interest. And what both of these encode, what both of these are talking about is that the value of money or the value of any resource, I'll just say money, changes in time. Specifically, you can consider this to be the time axis. And if this is now, usually you select the time of now to be 0. If that's now, then we can imagine, how much money would we have at some future time. Little t is equal to some time big T. That might be like a week, that might be a year. But more or less, the way it works is that here is P in both of these models. So P is here now, and this value, A, is over here. So this is, the name for this is called the present value. And the name for this one is the future value. And both of these models have the same property that when you're looking at it like this, what you're saying is that if at the present time I have P dollars and it is subject to this interest model, then after a time T, the future value will be A. So like the money as you move to the right is modeled by this. Whereas this one is saying, what if we have some future value, like say we want to have $100,000 in exactly 18 years. So we have $100,000 right here. And the question becomes, how much would we need to deposit exactly now so that that'll be $100,000? Well, conceptually that's saying, well, take that $100,000 and move it backwards in time. That's more or less the reason for the sign here. Notice that the sign there is positive. That is to say it's RT, whereas that one is negative. So this is the model that moves money forward in time, and this one backwards in time. All right. Good. Any question about this? Okay, good. Then finally, we have this idea of a money flow. And every time I say money flow today, that's going to mean continuous money flow. So a money flow is, well, it's like a paycheck. except a paycheck is not a continuous money flow, it's a discrete money flow, because you get paid at discrete events, you know, maybe weekly or bi-weekly or whatever. A continuous money flow is rather a different situation where if it's a paycheck type situation, that means that your employer has like a direct line to your bank account, and you know, pennies are trickling in all the time. That's what a continuous money flow is. So the event is continually happening rather than having discrete events. So in particular, a money flow is a function f of t, where little t is time, and f of t has units in dollars per time. And I write time because in different problems it might be different things. Usually time is measured in years in these problems, but you know, you can measure it in seconds. Okay. So here's the idea. So the first idea is the total value of a money flow. So the concept, the main concept, is that somehow you've got a money flow, and of course I mean continuous money flow. You can think of that like, you know, if you like to keep with the employment analogy, that's like your employer has a direct line to your bank account and pennies are trickling in all the time. Or if you like a physical analogy, you can just literally imagine that money's pouring out of a water hose. Whatever you like. But at any rate, the total value of a money flow, this is you accumulate all the money and you ignore interest. So that is to say, like, you know, it's a good idea to take your money and put it in a savings account. But in a sense, all of this money you could think is just being put into the bank of underneath your mattress, right? It's not there's no interest. It's not subject to any interest. All right. So if we have a function like this, so little t equals 0, little t equal big T, and if this is f of t, the money flow. All right. So what this means, what this red means, the fact that that's positive right there means that you're making money at that time. So you're making some money by virtue of that being positive. Because remember, what are the units of f of t? Money over time. So the units, money over time. So you're making money, but you know, maybe that's not that much money. And then as time increases, you're making more money. Like the money's coming in even faster. It's coming in even faster, and then that's when you're making the most money per unit time. But then it goes down a little bit, and you're still there. But you're making money the whole time. And how can you tell that at every instant you were making money? It's not that it's going up. What would it look like for a money flow that would mean you're losing money? Below, right? Below the horizontal. That's what that would mean. That means that instead of pennies coming in, if you like, pennies are going out. All right. So you're always, in this picture, you're always making money. Okay? what we want to do is we want to figure out the total value of the money. Now, if this was a year, and we like broke it into quarters, and there were exactly 4 payments, then it would be kind of clear what the total money was, right? You just take the 4 payments, and you just add them up. But this is a continuous payment in a sense. Right? So what we want to do is we're going to figure out how much money does this represent, and we'll take the strategy we just said. We'll cut this into quarters and say, all right, let's make an estimate for ourselves. So we cut the entire thing into quarters. Now, to make our lives simpler, I can see that in each piece, the rate at which we're making money varies. But just to make our lives simpler, I'm just going to assume that it's constant. Like, maybe this week, or week or whatever this is, quarter. Maybe this quarter we made, a rate of that much. So it's horizontal because we're saying it was that constant amount. Maybe that's like the average rate somehow. Okay. Then maybe in this quarter we made that much. That was our rate. And then in this quarter that much, and that much. So now, what I want you to do is consider. Let's have a look. Let's look at the rightmost rectangle. So in particular, I'm going to do a similar kind of thing that we did before. I'll say, okay, well, that constant value actually corresponds to this sample right here. And I'll call that, since that's in the 4th little bit there, I'll call that T4. Okay? And since we cut this interval into 4 equal pieces, that means that they all have the same size. So that size is the same as that size, is the same as that size, is the same as that size. So what's the total length there in time? Well, it goes from 0 all the way to big T, right? So that whole length is T. Yeah. So the whole length there is big T minus 0. And then we want each piece to be the same size, so we'll divide by 4. And then when we were doing something similar to this previously, we called the analogous thing delta x, but delta x is not a very good name today. What's a better name? Delta t is a better name, because that's the t-axis, right? So each one of these has a size delta t. All right, so let's have a look at the rightmost rectangle. Sort of zooming in on it, okay, it looks something like this. All right, so in the first place, what's the measurement of the base of the rightmost rectangle? Well, it's delta t, right? Delta t, and what are the units of delta t? Well, that's f of t, but delta t itself is just a unit of time, right? It's an interval of time. So this has units of time. So units. Time. All right. Now, how high is the rightmost rectangle? F of t4, right? Because the red indicates the height. It indicates f of t. And notice that we selected the rectangle that is the same as f at input t4. So the height of that rectangle is in fact f of t4. And now, what are its units? Money over time. Now, here's the thing, is that in calculus, usually we're just interested in like purely geometric things. So to go back to when we were doing this before, we were basically only interested in the area of the rectangle. Well, let's stick with that for a moment, and let's consider the area of this rectangle. Well, it'd be base times height, right? Now, I hope all of you have had the experience of being in a science class, like chemistry or physics or whatever. So now I'm going to write these things, but I'm going to include the units, which is to say that base times height, well, the height is f of t4, and then this has units. I'll write them in red of dollars over time. So that's its units. And then base, delta t, and of course that has units time. And then in chemistry, I guess especially, you're interested in dimensional analysis, which is to say, you want to make sure that the units, how do the units relate to each other. So at any rate, when you do this, what is the unit of the product? That is to say, just consider the red for a moment. Dollars, right? Can you see that time cancels? Yeah? So then, as a result, this is just equal to f of t4 delta t. That's the numerical value. And then the units are dollars. So what I'm telling you is that when we were dealing with this back in the day, this was just area. But do you understand that this rectangle is money? That's what this is. The area of it. So the consequence of this is that area is money in this consideration. Okay. So, well, each one of these pieces represents 4 bits of money, right? So money, 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 money. And what we want to do is we want to figure out the total money of the money flow, which is to say, with the water hose analogy, like there's money literally pouring out of a water hose, and we're just like pouring it into a bucket. And we want to know how much money comes out. Well, an estimate for it would just be to add up these 4 rectangles, right? The areas, I mean. So a 4 rectangle estimate of the total value of the money flow, okay, would just be the sum from I is 1 to 4, oops, of f of ti delta t. Well, I didn't mention it, but I suppose it's obvious. This is just considering the rightmost rectangle. Can we agree that the amount of money in the rectangle right next to it is f of t3 delta t? Okay. So similarly here. And then, of course, if you want to use in rectangles, there's nothing sacred about 4, except it makes for nice looking drawings. So suppose we cut it into n pieces. Okay, like that. Now, in real life, this is where it stops. Because in real life, I'm not aware of any financial transactions or banks or anything like that where the transactions are reckoned to be continuous. They're actually discrete, right? So like when you go to Walmart, there's an actual event where you swipe your card, right? It's not like a continuous, like, it's not like that. But, okay, whatever. So this is where, like, you know, when you go on in business, this is where it stops. But this is not business, this is calculus. So now we're going to say, okay, let's just continue imagining that, that it's continuous like that. Let n go to infinity. Then we have the limit as n goes to infinity of the sum from I is 1 to n of f of ci delta t is, okay, the same calculus joke that's as old as time now. We have a statement in Greek symbols. We're computing a limit. The Greek symbols become their corresponding Latin symbols. Here we have it. So, all right. The main thing I want you to take away from this is, you know, this is another way to do this rectangle game that we've played several times, so that's neat. But in the end, the main thing I want you to take away is this dimensional analysis thing. That is that if we have a money flow that's telling you how fast money is coming in units of money per time, like that, then area is money. That's what it is. Okay? All right. Now, what we want to do is we want to consider the following idea. And that is that, well, what if you were taking this money and instead of putting it under your mattress where there's no interest whatsoever, right? Because remember that the thing about this whole page is that we are ignoring interest. This is not a good way to deal with money. What if we took all this money flow and instead we were like pouring it into a bank account, right? That'd be better. That'd be better because, you know, the money that we get early, it would be subject to a lot of interest. The money that we get into in the middle, it'd be, you know, subject to about half as much interest. The money that we get at the end wouldn't be subject to much interest at all because we got it right at the end. But it'd be better than not putting it in an interest-bearing account at all. All right? So here's the idea that we want to explore. It is the following. It is called the present value of the money flow. So, we'll analogize this in two ways. One way is, I think I might have mentioned it last time, the idea is that, well, there's a lottery, right? Like, you know, the lotto, the things that people play and you hear like, oh, someone in Ohio won the $278 million lottery, you know, that one. Okay, well, if you ever buy a lottery ticket, then you'll notice that there's like several different things on it, but among the things on it is something called the cash option. So if you don't select the cash option, what that actually means is that if you win, and if you win like a big prize, like the 100 million jackpot, then they're not going to write you a check for $100 million. Rather, what they're going to do is they're going to pay you, you know, something like $35,000 a month for the next 120 months. And what that, the way that they come up with that number is they say, okay, well, the amount we're going to pay you per month for the next 120 months is if we took that money and instead of giving it to you, we put it into an interest-bearing account and nobody touched it, and we kept making all 120 payments at that amount, then after interest, it would be exactly the prize amount, $100 million. That's what that number actually means. that kind of idea, that kind of thing is called an annuity. So if you take the cash option, they're only going to make one payment to you, and it's going to be a big payment. But if you win the $100 million lotto and you take the cash option, it's not going to be $100 million. It's going to be, something measly that you can barely live on, like $35 million. You just scrape by. But it's going to be a lot less than $100 million. The reason why is because if you took that payment, the cash option payment, and you put it in that same account for 120 months, then at the end of that time, it would be the prize amount, more or less. Yes?
What would you choose?
The cash option.
You would?
Yeah. I think I can do better than the lotto. Hmm? Well, I mean, like, we're squibbling about what, I mean, in all honesty, is there a lot of difference between someone who has $100 million and someone who has $35 million? I mean, for some people, like, if you want to buy like, like a building, okay, maybe, but, I want to buy like a car, so like, whatever. All right, another way to think about it, besides the cash option thing, is maybe you're a business owner, like and you own like a hot dog stand or something, and you've got money coming in, and then and furthermore, you have a bank account and you intend to put all the proceeds of the hot dog stand into the bank account. Fine. Then the question is how much money would you be willing to take right now to give up the hot dog stand? 35 million, right? Okay, so then that idea is the present value. What would you take right now to give up that money flow? How much is that money flow worth to you right now? Okay, so that we have the following situation. Let f of t be a money flow. And suppose that we have a continuous interest rate R. I mean, really, like, who could spend $35,000 a month? Just thinking about it. I'm sure plenty of people could. I won't challenge you. But you're right. Okay, so we have this. What we want to know is that if you have a money flow and then you have an interest rate R, how much money would you give up? How much money would it take right now for you to give up that money flow? Here's the thing. The thing that we have to overcome. So here's time 0, and here's time big T, and here's the money flow. And here's the deal. So again, remember that according to the previous idea, area is money. So the money that is right here, if we wanted to transport it back, if we wanted to transport it back in time, that's some future value. We transport it back. It's worth almost the same, right? Because we got it very soon compared to when we started. But this money, we're going to take like a little block of money, and we want to transport it backwards to the present value, to the present time, so we can obtain its present value. So the main idea here is that we're going to, again, cut this into bits. We're going to, cut. And then we're going to take each piece of area and then transport it backwards to the beginning. All right. So now, to make things simple, what I'm about to do is not necessary to make it all work, but it kind of helps conceptually to make it all work out. Well, what am I trying to say? I'm going to try and make it like in agreement to where real world stuff works. But what I'm saying now is not strictly necessary to make it mathematically work. So again, we're going to cut this into 4 pieces. And you know, mathematically, what we've always said before is that, well, we'll just sample anywhere in there. Like if you look on the previous page, T4 was like in the middle for this one. Instead of that, we're going to make it to where we sample at the right endpoint. That just means that the height of the rectangle is going to be the rightmost point in the interval. But in principle, it could have been anything. So like that's the rightmost point. So that rectangle has that height. This one will have that height. This one will also have that height, and like that. So we're just selecting the rightmost point. So the reason for that choice is just so it kind of makes sense, you know, because you know, if this is like a month and you get paid weekly, well, then you get paid at the end of the week, at the end of the week, at the end of the week, at the end of the week. So you can kind of imagine that these are 4 separate payments that occur at the end of a week. All right. So, in particular, giving these things their common names, this one over here would be T4, this one would be T3, T2, T1. Again, looking at the rightmost rectangle, using the same kind of notation as before. This has a base delta t, and it has height f of t4. So the total amount of money that it represents is f of t4 delta t. And remember that the units of this is dollars. But here's the thing. Here's another time axis. If this is t is 0 here, and this is t is t4, then that means that at T4, we receive that payment. Like that's the end of that's a payment, if this is months and weeks, then that's the payment at the end of the 4th week. So what we received at this time was a payment of size f of T4 delta t. And what we're saying is that, you know, we're conceptually breaking this into 4 separate payments. And what we're asking is, what would you accept right now, instead of you know, to give up those 4 payments? So what do we want to do with this money? We want to take it from this point in time. This is some point in the future. Right? This is a future value. And we want to transport it to right here. So what do we want? We want the present value of this payment. That's what we want. So remember, the way the model works is that this is the present value, and this is the future value. And because we're talking about 4 separate payments, I'm going to just call this P4 and A4 to represent the present value of the 4th payment. Okay. So writing that, P4, when you want to solve for P, what's the formula? P4 is what? Mm-hmm. Very good. Yes?
So, are we going to just know the present value of one of the 4 payments and not the whole?
Just one payment right now. We're working on it one at a time.
Okay.
So we're conceptually, you know, breaking the whole thing into these 4 pieces, and then like furthermore taking this rectangle and sort of like mashing it down to a single instant where someone is handing you the 4th check. Like, there it is. So it all gets compressed to that one instant.
It's like what we've been
Exactly. So this is the, if you were to look at the fourth check, that's the amount that'd be written on it. Then the question is that the thing is that you're going to receive it at time T4. And what we're wondering is that, well, what if we took that amount and we transported it back to now? Transported it backwards in time to now. So that's the future value. We want to know its present value. So this is the formula to obtain that. So P4 then would be f of T4 delta T exponential of negative R T4. And the 4s just indicate that it's the fourth present value, the fourth time, like that. Okay? Finally, I'll do one more slight modification because this is how the book does it. The book commutes. This is the product of three things, right? Blah, blah, blah. So that's multiply, 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 like that. The book writes the delta t on the other side, so I'll write it on the other side. And all right, now I have a conceptual question before I move on. Why is that negative? Right, exactly that. It's because we're taking this that payment that's occurring at time 4 and pulling it back to time 0. That's why it's negative. That's why that's negative. Huh? Because we're asking the present value of the money flow, which is to say, if you had a hot dog stand and you were going to be making money continuously for the next year, the question is how much money would you take for it right now? How much money can I give you right now? And you just walk away and it's my hot dog stand. So the idea is that you're calculating, oh, well, I'd be making all this money, and then, you know, this is the good season right there where it's all real excellent. And you're transporting all that money backwards in time to right now. So we're saying, okay, we break it into 4 little bits of money. We have just explained how to transport that one piece. Can we agree that to transport the one at T3, it's exactly this, but with 3s instead of 4s? Okay, so what I'm telling you is that it looks like this. Is that we take this piece, the piece right there, and taking it back to time 0, the amount would be f of t1 exponential of negative r t1 delta t. That's how much money that would take it back there. So now let's take this payment and move it back. So it would be f of t2 exponential negative r t2 delta t. So that's moving the, that's the first check, pulling it back to time 0. The second check, pulling it back to time 0. The third check, let's pull it back to time 0. So the third check at time 0, and then we'll pull back the last check there to time 0. This should be a 3. Then T4, exponential negative R T4 delta T. So now we've pulled all the 4 checks back to the current time, and well, we want to know the total value, so we just add them all up, right? Just add them all up, blah, 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 blah. Now, we've talked about this negative. The negative in each one of those negative RT thingies is representative of the fact that we're pulling money backwards against the flow of time. Why is that a T1 and that's a T2 and that's a T3 and that a T4? Why are all those different? Yeah, because that just reflects that you're receiving payment at different times. That's all that means. So adding these all up, summing these things, we get a 4 rectangle estimate for a present value of a money flow. That would be the sum from I is 1 to 4 of f of t I exponential negative r ti delta t. Again, these two factors, the f of ti and the delta t, that represents the size of the money, the amount of money that you got at the time you got it. This exponential term, its effect is, and that's what it means to pull the money back to right now. Can we agree that the n rectangle estimate is exactly as this, but with n instead of 4? Otherwise, it's exactly the same. In the real world, this is where it stops. Well, it doesn't even do this actually. In the real world, when you do this, you don't pull it back with continuous interest. You actually pull it back with compound interest. So this is already not really reconcilable with the real world, right? Because interest is in fact not compounded continuously. If you wanted to do a similar kind of thing, but in the real world, we might get to it at the end of the semester. It's called, the idea is called annuities. But you can't, in the real world, you don't pull back with continuous interest. You pull back with compound interest. So you have to kind of keep track. Well, if I pulled it back that far, how many compoundings would it go through to do that? Whatever. So to get the exact answer, you let n go to infinity. So that's the limit as n goes to infinity. I is 1 to n, f of ti, exponential negative r ti, delta t, and, you know, second time we get to make the joke today. Right, we've got this Greek sum thing here, and then with the limit, and then the Greek letters becomes the Latin letters, and here we are. So this is a formula that you just must memorize. It's the formula for the present value of the money flow. And to sort of, you know, it's not rigorous math talk, but just to remind you of what we were talking about when we came up with this in the first place, remember this one is the cash option. How much money would you take right now? Okay. Now, just to make sure that some conceptual things are clear, is that if that exponential term were not there, then that's exactly the total value of the money flow, because the absence of that exponential term means that you're not moving around the individual bits of money through time. That this exponential factor there is representative of the fact that we're moving money through time, and in particular, you can see which direction are we moving it in time. Are we moving it forward or backwards in time? Backwards. How can you see that we're moving it backwards? Negative, right? Good. So this has been abstract enough for a moment. Let's do an actual exercise so that it's not a completely abstract day. So here's an example. Let f of t equals 75,000 t on the interval 0 less or equal t less or equal 3, and continuous 8% interest. All right, so what we want to find is we want to find the total value of the money flow, and we also want the present value of the money flow. All right, now before we start going for the answer, I want to do just some discussion to make sure that you don't lose track of the main ideas here. Could you please remind me, what are the units of f of t? Right. F of t units are money over time. So don't lose track of that. What that's saying is that, for example, if you were to evaluate f at 0, then what do you get when you plug in 0? You get 0. What that means is that, you might imagine that this is some kind of business that you're just starting. And, well, it's not an excellent idea to start a business with no income, right? It's better to start it with a few customers, but, you can imagine if you were to start a business, it might be the case that, in fact, you don't have a customer yet. So then your current money flow is 0. So like when things begin. Okay, and if this is dollars, like 75, if 75,000 represents dollars and t represents years, this would mean that you're making 0. Your instantaneous rate is $0 per year. Now, what about say at half a year? What if you were to plug in half? What would you get? Yeah, you get 3,7,500. So 37,500. Now, what does that mean? What is the meaning of that number?
There's 6 months, you can do $7,100.
It doesn't mean that, actually. It doesn't mean that. This is your instantaneous rate. That means that if everything were to just be constant from now on, like the business is completely changing, but if suddenly someone snapped their fingers and then nothing changes from now on, that means that from now on you would make $37,500 a year. If someone makes $37,500 a year, you can boil that down to you can divide that into minutes, right? Such a person makes, I don't know, 20 cents a minute or something. I have no idea. Okay, but that's how much you'd be making. So this is the rate at which money's coming into the account. All right. What about at f is 2? Well, if you plug in 2, you get 150,000. Does that mean that they've made $150,000? No, right? What that means is that's how fast money's coming in right now, $150,000 per year. That's how fast it's coming in.
What is the 2%?
Years. So units are dollars per time, and if we say that if we just say, the exercise doesn't say, but if we just say that t is in years, then the meaning of this is that at t equal 2, we're making, just at that particular instant, we're making $150,000 per year in business. Okay, and then at 3, that'd be 225. And what that means is that your business would be making, the rate, you'd be making $225,000 per year. So what this is that it's a business where you start out making no money, and then you're making more and more and more money all the time.
So this doesn't mean the amount of money you,
No, this is how fast it's coming in.
so they all the same.
What's all the same?
Like the rate. They make me $75,000 a year.
No. 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 How do I, what do I say? What am I trying to say? No, it's that, how fast, well, I mean, let's just, I'm a mathematician, so everything, when I get a question, everything falls back to geometry. Let's just plot what this looks like. If you were to plot this, and this is the t-axis, then how does f of t look when you plot it? No, f of t.
Oh, it is a straight line.
Is a line that goes through the origin and has slope what? 75,000. Right? So it looks like this. So this is f of t, like so. So the question of how much money have you made to date? So like, for example, if we consider the specific time 2, here is t is 0, and say over here is t is 2. Then what this measurement is saying is that how tall is this? How high is that? It's not $150,000 because what's the units of f of t? It'd be dollars over time, dollars per year. So this would be $150,000 dollars per year. So that's f of 2. Now, a separate question of what is the total receipts? How much has come in from time 0 to time 2? How do you answer that question? Well, that's this, right? That's that area. So what I'm telling you is that that represents how fast money is coming in at that instant. That is how much money you've actually made, that area. You got it?
Oh, yeah.
It's a little slippery. You got to keep track of it.
Yeah, so you don't count the line. Oh,
No, because that's the curve is this green line.
okay. You only count the area.
Right. Yeah, the integral. Yeah. Okay. Good. So blah blah blah. I lost track of what I was saying. Finally, before we move past discussion, because we haven't done any work yet, right? Besides, we haven't done work towards answering the question. I mean, finally, these are two different values: the total value of the money flow and the present value of the money flow. What is your expectation concerning their relative sizes? Okay, so expectation of total value versus present value. Okay, you say that the present value should be smaller. Why?
Because money tomorrow's, you would be willing to take smaller money now because it's going to gain interest over time.
Right. In the end, remember that interest is just about, what it is, it's an agreement and representation of how much it's worth to be in control of the money now. Right? So you could say that, well, perhaps this hot dog stand in the end is going to be worth $500,000, which is to say that we're going to have $500,000 of income over 3 years. Well, what if someone were to walk up to you and say, I'll give you $350,000 right now for it? That's the question that you're trying to answer, right? Because if they say, how much money would you be willing to take right now? And you say, well, I expect to make $500,000, $500,000 over the course of 3 years. And they'll say, I'll give you $1 million right now. Okay, you can have it for $1 million. Right? I would have taken less. You get the idea? The amount of money, the present value, should be less than the total value. Alternatively, you could ask, you can say this in terms of the lotto, and that is that, in some sense, the lotto, what they're advertising to you is the future value. And then if you take the cash option, can we all agree it's going to be less than the advertised value? We haven't talked about the future value yet, but we will a little later. Okay, so then let's do it. The total value of the money flow. And the thing to remember about the total value exercise is that there is no interest. And you must memorize the formula. The formula is integral 0 to big T, f of little t, d little t. So that's something you just have to, that's a memorized thing. Fine. So in this exercise, we said what f of t was. So this would be integral and then 75,000 t little dt. And then 0 to, now what's big T in this exercise? 3, right? Good. So in the end, for the first question, this is the answer is whatever this is. Okay. So then remember, the integral is homogeneous, so that 75,000 to that extent can be ignored. And then we'd love to use the fundamental theorem, which is to say, can we think of an antiderivative of t dt? Well, can we? Yeah. Okay, so then that'd be t squared over 2. The division by 2 makes that 3,7,500, and then t squared. Now we have to do the boundary evaluation from 0 to 3, like so. Remember that when you have an expression like this and you've got a constant right there, that constant can remain factored out. 37500, like that. And then we'll evaluate just the non-constant part at each place. So that'd be 9 minus 0, like so. And then it would be a good idea for you to try to get your calculator to work, because next week you're going to have to do it to the nearest cent. I mean, obviously this is not that difficult, but pretty soon when we're dealing with interest, then the numbers get entertaining. So that number is 337,500. So what that's telling you, so what you tell me, what is the meaning of this number? No. That's a different matter.
Oh, I'm sorry. That's how much the hot dog's going to be worth after 3 years.
Okay. So specifically, if we imagine it like this, like you've got the, you're taking money, it's all cash. Okay, let's ignore all the other things. Okay, and then the register is literally like just there's just like a bucket, like when you put money in there, it just goes into a bucket. And you didn't do anything with that money, you just kept putting it in a bucket, just blip, 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 every time it went in the register. If you counted it up, that's what it would be in the bank of under your mattress, right? No interest involved. So that's the total value of the money flow. Okay, now what we're going to do is we're going to compute the present value, which is to say that now the register, instead of just being hovering above a bucket and we're just pouring money into the bucket and doing nothing with it, actually what's happening, you can imagine that it's all being transported back to the present. Okay, and when money transports back to the present, it shrinks in value. So what's our expectation about the present value of the money flow? Should it be more, less, equal to this? Should be less. All right, let's verify that. So the present value of the money flow, again, this is an integral formula you must memorize. So this is integral 0 to t, f of t, but now exponential negative rt dt. That exponential factor is representative of pulling all the pieces as they come in back to time 0. Okay, so on this particular problem, that's integral 0 to 3, and then 75,000 t times the exponential of negative. Now, in this problem, what's r? 0.08, because it's a continuous 8% interest, and you have to remember that r has to be a decimal, so 0.08. T dt. So in the end, to finish the question, we have to answer this. All right, so is there any question why, in the end, this is what we have to evaluate? All right, so a couple things I'd like to remind you of so that we can make it through this without too much pain. We know exactly 3 antiderivatives, yes?
On the parentheses, this is supposed to be round all of it. Like we went over last.
I'm not sure.
Like the parentheses is supposed to be around, so it's not just multiplying.
It doesn't matter because it's all, I mean,
it's all connected.
yeah, I mean, it's
Yeah.
that thing times that thing times that thing times that thing. So it's the product of 4 things. It's kind of weird that that's an exponent. Like in my heart, when I'm writing that, I actually think of it like this. Because it looks better to me like that. But that's not how it's written in the book, so I write it like that. But whatever. This is what when I'm dreaming about my faraway place. Fine. So we want to use the fundamental theorem, which means we want to compute an antiderivative. How many antiderivatives do we know? Just 3, right? So let's just review those real quick. Well, one of them that we know is the antiderivative of x to n dx. And every time I think about it, I am always amazed and surprised that, in fact, it works for every n except -1. The formula is x to n plus 1 over n plus 1 and then plus a constant. The formula sort of tells you at least a reason why it could not possibly work with n is -1, because that would amount to a division by 0. Well, in the specific case of -1, we're actually still able to proceed, but the rule is kind of unexpected. What is the answer when the exponent happens to be -1? The log one, right? Right, log absolute x and then plus a constant. There's beautiful and deep reasons why it has to be this way, but we don't talk about it in this class. What's the other one, the last one? The exponential one. Now, here's the thing. Each one of the ones that I'm writing down here, of course, they're representatives of a whole family of things. What I mean is that, like here, from here to here, we used the fundamental theorem, and in particular, we used the power rule. Now, that 75,000 is not written here, but the integral and the antiderivative are homogeneous, so it comes out. Right? And then you can put it back in, however you like to think about it. But at any rate, that's that rule right there. Well, the exponential rule is, remember that it is representative of a whole family of things. So in particular, I want to remind you of one that will be of great use from now on for us. And that is, what if we do the antiderivative of the exponential of, instead of just x, what if we do a constant like k multiplied by x? So you could reimagine this one as, 1x, exponential of 1x. Here I'm saying exponential of kx. Well, then what's the answer? Mm-hmm. Very good. Exponential of kx over k. Of course, the requirement is that k is not 0 and constant, and it is constant. Okay. Good. That's a particularly useful one to know, rather than trying to figure it out every time with a substitution. Okay. So again, just remembering those things, this is what we want to evaluate. So, remember the Riesz procedure, which tells you how to evaluate an antiderivative. So ignore the fact that it's an integral for a moment and just ask, is this exactly one of the three that we know? Really? It's not like the kx one? It's not that one? No? Why not? Ah, yeah, we got the extra t there. Okay. Notice that this rule doesn't have an extra x floating around anywhere. Okay, so this is not precisely one of the three in the end because of that t. We can smuggle the 75,000 out, but you can't get the t out, that t. Fine. So then, is there something algebraic we can do to simplify matters? Not really. We can get the 75,000 out, but you can't get the t out. Now, t can't go outside because it's this procedure is with respect to variable t, so it can't go out. Okay. Could we do, what's the next step, if not algebraic? Right. Can we do a variable differential substitution? Well, can we? In the end, the answer is going to be no. So I know that y'all have done substitution problems where it looked kind of like this and it worked. But in the end, that was because that t right there in the exponent was a t squared or something like that. And then you made this whole thing u. Now here's the thing. If you're going to do a variable differential substitution and you say u is some polynomial and it has degree 8, then what else do you need to be looking for? A polynomial of degree 7. Its derivative hanging around somewhere. So here's a polynomial of degree 1, that constant times t. Well, you can see that you would want the result to be a polynomial of degree 0, but it's another polynomial of degree 1. So the fact that, if that were degree 2 and degree 1, we could do it. Or if it were degree 10 and degree 9, that would work. But it's not going to work. Okay, I have a question. What about this? So What about this? Would we be able to do it like this? So the antiderivative we're dealing with kind of looks like this, sort of simplifying it. You know, if we just kind of get rid of all the constants, kind of looks like that. Would this work? Just to say like, well, I don't know, I'll anti-differentiate each one of the factors. Does that work? No, that won't work. It can't possibly work.
You do that, adding and subtract something.
I'm not sure what you mean.
If instead of multiplication, it's like subtraction and addition.
Ah, you mean
T plus
you mean if that were a plus,
Yeah.
then it would work, because this green dot is that green dot, and if it were not a dot, a multiplication dot, if it were a plus, it really would work, because the antiderivative is additive. If it were this, which it is not, then it would be called multiplicative, but it is not. So let me ask. You know, the reason why this couldn't possibly work is because, well, in the end, if we were computing the time derivative, say, of the product of u and v, so u and v each being functions of t, then isn't there some kind of rule that tells you how to compute the derivative of this product? Yeah, what is the name of that rule that tells you how to compute the derivative of a product? Yeah, the product rule, right? That's right. So then du dt, and then multiplied by v, plus u multiplied by dv dt. So now, does that mean you just compute the derivative of u, the derivative of v, and then you just multiply them together? No, right? This is correct. And remember that antiderivative is doing derivative backwards. So because derivative doesn't work this way, neither possibly could antiderivative. It doesn't make any sense. Nevertheless, I noticed a couple of responses to questions that looked like this. Well, that being said then, we're still trying to do this. What is the next step in the Riesz procedure, if not a variable differential substitution? By parts, right? And by the way, every antiderivative rule corresponds to a derivative rule, which the antiderivative rule by parts corresponds to what? The product rule. What I'm trying to get you to see is that, do you observe? That's a product. Well, I hope that it is like natural that we should use the antiderivative product rule, whose name is antiderivative by parts. Good. All right. So to remind you of all those things, we have this acronym LAE when we're doing by parts. Here's the, just copying that integral so I don't have to keep referring to that other page. The formula for antiderivative by parts is u dv is uv minus antiderivative v du. That's when you're doing anti-differentiation by parts. But we're not doing anti-differentiation by parts. We're doing integration by parts because this is an integral. So you need to know, you need to make sure that you understand that one as well. So right now I've just copied it down, and my question is that how do we modify the antiderivative by parts to become integral by parts. So if this is an integral, a to b, then, well, it stands to reason that needs to be an integral too, right? So this should also be a to b. Most students can get that, but there are some bits that the corresponding change to this is often left off. So how do we, what modification is necessary for this one? Right. You have to do the boundary evaluation, a to b, like that. So this formula on the top is antiderivative by parts, and this one is integration by parts. Okay. So when you're trying to get all the things worked out, we have this acronym LAE. What we're supposed to do is we're supposed to take all the factors and label them corresponding to their category. So here is a factor, 75,000 T, grouping those, the constant with the T. What kind of label does that one receive? An algebraic label. Okay, and then this exponential factor, what label does it receive? Exponential one, right? So then in the by parts heuristic, what you do is you choose, you label all the bits, and you choose whichever one is leftmost, whichever one comes first in LAE, which is A in this case. So A is going to be what? U. So U is 75,000 T, and then dV is always automatically what? Everything else. So exponential negative 0.08 T dt. So here's the thing. When you use by parts, either antiderivative by parts or integration by parts, what I want you to observe is that there's exactly 4 terms. There is U, dV, du, and v. And I want it to, when grading your stuff, I want them all to be very clear, like 1, 2, 3, 4, there they all are. So what, we have 2 of them, there's 2 more to go. What can we get from du, from u? du, right? So we can differentiate this and obtain that du is 75,000 dt. What can we obtain from v? Man, I'm having trouble, all right. What can we get from dv? v, right? We can get v. The way that you get it is you anti-differentiate this. So exponential negative 0.08 t dt. And when you're doing by parts, this is one of the moments of truth, right? Where you have to ask yourself, well, am I going to be able to keep going? Because if you can't do this, you've got to do something else. Well, can we do this? It is, right? Notice it's exactly that one that I mentioned on the previous page. This is exactly antiderivative of exponential kt dt, with k is that number there. Okay. So the answer is exponential negative 0.08 t, and then divided by negative 0.08. Now, do I need a plus c? No. The reason why no is that, well, if we were doing antiderivative by parts, then at the end of this step, there would still be more antiderivative to go. We'd still have to do that one. So it wouldn't be time for a plus c yet. And even still, we're not doing antiderivative by parts. We're doing integration by parts, and there is not a plus c when you're integrating. Or if you like, you can always select the c to be 0. Fine. So as a result, the integral continues to uv, so 75,000 t, that's u, and then v is that thing. So exponential of negative 0.08 t over negative 0.08. So that's uv, and then the formula says we need to do the boundary evaluation on this, so 0 to 3. So that's uv 0 to 3, and then minus integral 0 to 3, now v du. So that du. Okay, any question getting here? Again, this is where your calculator is going to start coming in. All right. Now, before we get any further, it's probably a good idea to, simplify some stuff as much as we can. So, in the first place, I'll divide 75,000 by that number. And get, so that becomes negative 937,500. Then t, then exponential of negative 0.08 t 0 to 3. Again, I didn't do the boundary evaluation yet. All I did was simplify that a little. Then that same division is right here, right? So that same number will show up, 937,500, and then these negatives will cancel, right? So that it becomes plus integral 0 to 3, 937,500 times the exponential of negative 0.08 t dt. Any question getting here? Again, I haven't done much. I'm just trying to set myself up for success. To pull that out? Yeah, I mean, I could. It'd be fine. But I'm just going to do this part separate and then that part separate. So to evaluate just this part, remember that's a constant. So I'm going to leave it factored out. I'll leave that constant there factored out and then do the boundary evaluation just on the non-constant part so that it becomes negative 937,500 multiply by, so now that thing evaluated at 3, so that'd be 3 times the exponential of negative 0.08 multiplied by 3, and then minus 0 multiplied by exponential of negative 0.08 times 0. So that's just the boundary evaluation thing. That's just that part. Then plus 937,500, because we're integrating and that's just a constant there. Is that one of the antiderivatives we know? Yeah, right? It's like exactly the same one we've done once already. It's that one. So this would be exponential of negative 0.08 t over negative 0.08. And then this needs to be evaluated 0 to 3. All right, so I'll type that monstrosity into the calculator. In fact, it's kind of easier than it looks, right? Because that's a multiply by 0, right? So in fact, you don't need to type that part. You just need to do blah blah. That. I'll do that. Okay, so then now would be a good opportunity for you to see if you can get your calculator to do the same thing, right? Because eventually it's going to, you know, be between you and the machine. So typing that in to the calculator there, I get the number that. Okay, so then I'll write that down. So that's a negative, how many is that? Negative 2,212,390, and then 859. And I'm going to leave it unrounded because you only round at the end. Now, it's at least momentarily concerning that we've got some number that's negative 2 million. That seems kind of strange. But remember, we have yet to evaluate this one. Okay, so then I'll hold my concern for the moment. So this will be plus, and then now I'll evaluate that constant. Okay, so that'd be plus negative 1,171,750 times the exponential of negative 0.08 t, and then I still haven't done the boundary evaluation yet, just preparing myself for it. By the way, the convention I use is I never write commas when I'm doing math notes. Rather, I just write spaces. So that means 2 million, those are the millions, the thousands, the hundreds, etc. All right, doing that now. So that'd be negative, well, it'd be negative 2,212,390.859, and then subtract 1,171,750, and then now multiply by that. So it would be exponential of negative 0.08 multiply 3, and then subtract exponential of negative 0.08 multiply 0. So this second one is actually easy, right? Because negative 0.08 times 0 is 0. So this is asking what is the exponential of 0? Well, what is it? It's 1, right? So it's really that number times that exponential minus 1. All right? Oh, I appreciate that, but I'm okay. I appreciate it. Okay. So, negative 2,212,390.859, and then subtract negative 2,500,000. 454.753. Okay. So adding those two numbers together, I get, rounded to the nearest cent, I get $288,063 And then to the nearest cent, 89. Okay, so a couple of questions. We've done all this careful work here, and we came to this number. What does this number mean? Okay, that's its name, right? This is the present value of the money flow. And if we call it a hot dog stand, then this is the present value of the hot dog stand. Now, does this number make sense in light of the previous number that we found? So remember, back in the day when we started this question, back when times were different, we asked for two things. We asked for the total value of the money flow and the present value of the money flow. Okay, so then we determined that the total value of the money flow was that number, 337,500. And what we're saying is that the present value of the money flow is this, 288,000 whatever. Do those numbers make sense? Okay, if no, then why no?
The present value has to be less than the total.
It is. The present value is 288,000.
Wait, how do we get from
It's 8%.
Right. So what we're saying, is that, well, if I were to be the owner-operator of this hot dog stand here, I'd expect at the end of time to have collected $337,000. But if you were to give me $288,000 right now, I'll take that and just walk away. It could be your hot dog stand. This is how much I'll take right now for it. Now, it's less than how much I expect to get. But what accounts for that being reasonable? Interest, right? Because here, in this situation, is that you're taking control of this money as it comes in. Right? You don't get all this money right now. In this situation, it's I'll write you a check right now. I'll just give you bags full of money right right now, and you can take control of the money right now. You can have it. Okay, so the fact that this represents you taking control of the resource now, and this means that you're gaining the resource over through the course of time. That's what covers the difference. That's why this one is less, must be less. Yeah, yes. This is a $100 million lotto. That's the cash option. Okay, it's less, but you get it now. Good. Any question about this? All right. Now we're going to start one more idea, and then we'll have a quiz. So we won't get entirely through this idea. So now, besides the total value of the money flow and the present value of the money flow, which we've talked about, what the present value is it's saying, okay, well, a money flow is where you get little bits of money, but the receipt of the money is through time. The present value is the thought experiment which says, let's transport all of the money back to the beginning. That's the present value. If instead of transporting it to the beginning, we transport it to the end, then that's the future value of the money flow. Okay? That is to say that if you're running the hot dog stand, instead of just putting it into a bucket or under your mattress or whatever, what if it goes directly into an interest-bearing account? Then what would the number be? How much money would you have? So 337,000 was the total value. That's without interest. The future value is saying, what if you were putting all that money into an account exactly when you received it? Well, then the future value would be more than that, right? Because it would be subject to interest. Okay. So again, let f of t be a money flow. And suppose that we have continuous interest R. Now again, the idea is that we're going to take all the little bits of money, and remember that conceptually area is money. So we're going to take all the little bits of area, and instead of transporting them to the left, backwards in time, to t equals 0, we're going to transport them to the right, forwards in time, to t equal big T. Now, that being the case, what should you expect about the sign on the exponential? Should be positive, right? So before it was, we had a factor that said exponential negative RT. Now it's going to have to be exponential and then positive something or other. Okay. So same idea, is that we take this, cut it into pieces. And again, just to make our lives simple, we'll say that, okay, we've discretized it into these discrete payments, and the payment occurs at the end of the interval, which means that the height of the rectangle is the height of the function at the right endpoint. That's just to make our lives easy. Okay, but in the end, that's an estimate, right? Because remember, money is area, and we can make our estimate more accurate by using more rectangles. Now, calling that payment right there T1, the first payment, represented by that first rectangle there. So if we look at the leftmost rectangle, well, using the same kind of notation that we used before, this is delta t, and then what's its height? That's the units of the height. It'd be f of t1, right? So what's happening here is that this represents a payment of size f of t1 delta t. And remember that the units work out because this is money per time, and that's time, leaving units of just money. So here's the thing, is that here's T0, T is 0, and here's T is big T. What we're talking about is we received an amount of money right here at T1. And we want to move this money, instead of moving it to the left, to the beginning, we want to move it to the right, to the end. So we want to move it forward in time. So we're going with the imagination that we happen to be at time T1 currently. So this is a present value. And then we want to move it forward to the future. So how far in time does this money need to travel? Yeah. If the final time is big T and the current time is T1, then it should be big T minus T1. That's how far it has to go. We got to move it forward. All right. This is a present value. I'll call it P1 because we're talking about payment 1. We want to know its future value, A1. So we want to use the formula. This is the one we want. So this is the one we have. This is the one we want. So we want the formula that has A solved for. So how does that one read? Very good. And I've made I made A have subscript 1, P subscript 1, and T subscript 1 because we're talking about the first payment. Now, what do you notice about the exponential? Right, that's positive. That, oh, this is not right, actually. That's not right. Because, in fact, this needs to be how far forward you moved it in time. So the distance that in time that we moved it forward was t minus t1. So big T minus t1, like so. Now, I want to do a little bit of algebraic simplification, and then this will be the last thing that we do today. So notice that, well, just distributing that r, we get r big T and then minus r t1 like that. That's just distributing the r. And now, when you have exponential of a minus b, you can actually turn that subtraction in the exponent into a product in the base, so that it looks like this. A1 is P1 multiplied by exponential of r big T, and then now multiplied by exponential of negative r big T, r little t1. So what I used here was that the exponential of a plus b is the exponential of a multiplied by the exponential of b. That's what I used right there. So now, I'm going to write one more thing and then say something, and then we'll have a quiz. So now P1, the present value of that payment, is that value right there. So the formula that we're looking at is this one. I guess I really want to write one more thing, otherwise the thing I want to say will not make sense. So I'm going to move this factor to the front, the one with big T. And here's the secret sauce of it all. So notice that if I cover up that factor, the one with big T, then isn't that exactly the thing that we were using for the present value? It is, right? Because what that's doing is that exponential with the negative in front of it, that's moving the money backwards in time. That's what that one's doing. And then we've got this with a positive thing that's moving it forward. So there's we can't make it completely clear what's happening here and now. We'll make it clear on Thursday. But what I want you to see is there's kind of a tug of war. Is that this exponential is taking the money rectangle and wanting to pull it back to the beginning. And this one, more or less, is taking it and saying, nope, actually I want to push it all the way to the end. Interesting. Okay. So any questions before we have a quiz? Yes?
Just to strategize now, for the final, will we have like the regular final length?
Actually, pardon me. Actually, as I understand it, we're going to have the final on the last lecture. So it's going to be 2 hours and 15 minutes. It'll be exactly the length of a lecture.